In this first video about the divergence theorem, we set up the preliminaries for what has to happen in order for us to be able to use it. Remember what we have right now. We're doing flux integrals. So we've had a vector field that's always been of the form f1i plus f2j plus f3k. Remember, f1 is just a formula. It can have x, y's, and z's. It's just the stuff next to I. f2 can have x, y's, and z's. It's just the stuff next to j, and similar for f3. Now, what we've been doing is we've been looking at surfaces that usually have giant holes in them. Now, what do we mean by having holes? Well, basically, there are boundary points on our surface. Remember, a boundary point is a point where every time you try to draw a circle, you hit stuff on the surface and hit stuff not on the surface. What we want are what's called closed surfaces. Now, closed curves were easier to define. We want closed surfaces. And what we mean by a closed surface, it has to be bounded. In other words, we have to be able to draw a box around it, or a giant ball. It also needs to be closed. And for us, what that's going to mean is there are no boundary points for the surface. Now, how can you not have boundary points for the surface? Think of a sphere, right? Every time I pick a point anywhere on the sphere, I can actually draw a little tiny circle that stays on the sphere and only on the sphere. So a sphere would be an example of a closed, bounded surface. There are others that we've actually seen stuff like. For example, if I have a bowl up here and a cone down here, it's still closed because there are no boundary points. Every time I pick a point on this surface, remember, not on the inside, but anywhere on the surface, I can draw a little tiny disc, and the disc stays on the surface the whole time. It's also bounded because I can draw a big circle around it. So those are two main examples of closed bounded surfaces. Ones with like a sphere that seem to be closed naturally, and the ones that maybe had holes and we actually close them by capping them, the way this does. So what we want to be able to do is start with a closed bounded surface. Let's just draw the one we just did. So it looks like this. Now that one it looks like it has a giant hole, but the cone actually fills it in. And what we want to do is measure flux out. So that's the surface. Now this is actually what they needed to actually start defining charge. And strangely enough, what we're going to do is approach this the same way we actually approach Green's theorem. Remember, with Green's theorem, we had a closed curve, and instead of actually doing anything with the curve, we drew a little tiny rectangle on the inside, calculated the work done around the little box, and then added up all the little boxes. And because of telescoping sums, all we were left with was the stuff in the boundary. This is going to be very, very similar, except what I'm going to do on the inside of this giant ice cream cone. So on the inside, we are going to draw a 3D box. And what we're going to do, not calculate work, we're going to calculate the flux out of that little tiny box. So the next whole video is just calculating the volume, the flux out of that little tiny box, right? And after that, we'll add them up and see what's left. So that's actually the setup. We have a vector field that's velocity, we've got a closed bounded surface, and we're going to draw a box on the inside of the surface. Not on the surface, but inside the surface, and calculate the flux out of that one little tiny box. Onward to our calculation.